Hello, this is Nicolas from INSBU. In this video, I'm going to show you a demo of AFD and DPP on Nexus 9K. The video assumes you are familiar already with the concept of AFD and DPP. What we are going to have here is Nexus 93180 with a few ports connected to a Nexia traffic generator, right? So we have 3 downlinks and 1 uplink. Okay, so this is the switch. So from the configuration perspective, those are all fairly standard routed ports with no specific configuration. Okay. What we're going to do here is first send elephant flows. So we have a Nexia on the other side somewhere from the uplink. So it's a 40 gig link. So we're going to be sending 16 gig of bandwidth through that one, all going to the port 143, which is a 10 gig port, right? And we're going to send long-lived flows, just 2 of them, for a total of 16 gig. And those are going to be our elephant flows for the demo. So if you look at the uplink, we see the input rate is indeed 16 gig, right? But of course, those elephant flows will be dropped because there's not enough capacity on the downlink to handle them. So we see here the output discard keeps increasing, right? And of course, with TCP would adjust, right? But what we're going to show here is how we can manage the buffers so the elephant flows take only a reasonable amount of the buffer and leave sufficient headroom for microbursts to be absorbed. So let's take a look at the QS statistics. So we're going to clear the QS statistics, and at the moment we have no specific QS configuration. I have the AFD policy mapped, I have prepared, but actually we're going to remove it, right? And so here we make sure there is no specific QS policy applied anywhere. It's only defined, but it's not applied. And so we're going to clear the QS statistics and look at the queuing information for the downlink, right? So what we see here is the default group is QS group 0, and so we see all packets going there, right? And all drops happen in QS group 0, which is fine, right? This is expected. We're going to clear the counters for the buffers, and I have defined a CLI show buffer that essentially does the show hardware internal buffer command. So let's take a look at the buffers, right? Here we see the slot 1 is just the switch, instance 0 is the first slice of sugar ball, and here interface 143 is part of the second slice, and so that's why you see there is no buffer used at all in this slice, and so that's why we're going to skip it and just we're going to go to instance 1. And what we see here is at the moment the CLI was executed, we had 59,000 cells used, and the peak was also 59,000, right? Because we're constantly sending from Nexia, so the buffer is constantly used, right? It's not totally used because we have some queue limits dynamic mechanisms to make sure there's still a little bit of space, but you see a big part of it is consumed by those elephant flows, right? And we can see here in Q0, the port 38, we could, with the show internal command, it indeed maps to 43, right? And so here we confirm lots of buffers are being used, right? The cell size is 208 bytes, 208, right? So here it's consuming around 12 megabytes of buffer. Okay, so now we're going to try to send a microburst. So what we're going to do is we're going to take 2 downlinks, 41 and 42. Those are all connected to Nexia ports. From the 2 Nexia ports, from each port we're going to send 10 flows simultaneously, and each flow is going to be 5,000 packets of size 128 bytes at 1 gig. So this will result in a microburst of 6.2 meg at 10 gig from each Nexia port. right? So you see the ports destination, and they will all both go to 143. So here essentially we are trying, not only the port is already congested by elephant flows, but the burst by definition, we are trying to fit 20 gig of capacity into a 10 gig port, right? So there's not enough capacity. Now the whole concept is, let's see how AFD can help us. But we're going to see first of all, without any AFD or DPP config, let's see what is going to happen. So this is the XR configuration. Those are the XR interfaces, right, with the gateway being the interface, okay? And those are the XR traffic items, right? So as I said, we have 10 bursts from each port, right? 141 to 143, 1 to 10, and the same for 42, okay? And we can confirm how the traffic is defined. Frame size 128, the rate is 10% of 10 gig, which is 1 gig, and this is 5,000 packets. And we have the flow with the correct source and destination address, okay? And we just keep doing exactly the same for the different flows, right? From 41 to 43, those are the same, and the rest are 42 to 43, okay? So we're gonna go ahead and send this microburst and see what happens. Right, so as expected, the microburst was not able to fully go through. There is more than 70% of loss for each of the flows. Right, and this is because we had the elephant flows were consuming a big portion of the buffer. There was a little bit left, but not enough for the microburst to be absorbed. So we're going to clear the statistics, and now we're going to go back to the switch, and actually we are going to enable AFD. So I'm going to my QoS policy here. We can keep using the default queue. This is fine. But for that queue, we're going to enable AFD. Okay. So now the microburst is stopped, but the elephant flows are still going through, right? We still have the 16 gig traffic that is going, and we still have, you know, that elephant flow going out of the port 43, right? So we have a CLI. This is a Python script I have written to display in a readable view the elephant flows. The switch now is able to detect elephant flows, and so we can check that we should have 2 flows, right? And indeed, those are the flows we send from a different XR port. And so we see our 2 elephant flows are indeed recognized by the switch. But now if we compare, right, let's look at the buffer now. The buffer usage we used to have was important because the elephant flows were not recognized as such, and so the switch was not doing flow aware QoS, so it didn't know. So it was giving a large amount of the buffer to the elephant flows. But now, if we again do show buffer, oh, I forgot to actually enable the QoS policy, so it didn't take effect. So system QoS, right? And now we're going to do, oops, so we're going to do service policy type queuing output with the AFD policy, right? So now AFD is part of the policy map, and we have applied it to the whole system. And of course, you could also apply it with an interface granularity. And now if we look at the buffers again, we can see here that for the second slice, where 43 resides, the instant usage has dropped significantly, right? And we can see it's still Q0 and still the same interface. But since this is elephant flows, the buffer usage is very little now. Is very little. So now we can simply go to, so we're going to clear the buffers because we're going to resend the microburst, and we want to make sure, we want to see how the burst is going to be absorbed. But we can see here with EFD the peak of the cells used is very little compared to the total amount of buffer. So essentially we are leaving enough headroom for the burst to be absorbed. Okay, so let's go back to Exia. Remember last time we had around 70% of loss for the microburst. So we're going to go ahead and send the burst one more time. And you see now there is 0% of loss because RX frames were all received. Okay, and so that fairly big burst was actually absorbed entirely by the switch. And so now if we check the buffers again, so again let's skip the first slice and look at the second slice, right? The peak cells, right, was 50,000. Okay, so we used the additional headroom that was left that was left to absorb the burst. Now of course the instant usage is back to a low level because the elephant flow is gone, but we see how the peak cells, the peak buffer was used to absorb the microburst. Now, and we can do something else now. We can enable DPP, the dynamic packet prioritization. What it does is it's going to take the first few packets of the mice flows and put them in a different queue. Typically, you want to use a strict priority queue to make sure, especially the first few TCP frames are going to be given the highest priority. So, in addition to AFD, let's enable DPP. So, we're going to do a policy map type. So it's a different type. This one is network QoS, and let's call it policy map DPP. We can use the default queue, and what we're going to do is for the mice flow packets, those first few packets, we're going to say we're going to put them in queue 7, which is the strict priority queue. Okay, so we do that, and let's go to system QoS, and let's do the service policy type network QoS with the DPP policy. Okay, so now we have both AFD and DPP enabled. Let's clear the QoS statistics, and we will resend the microburst flows and look at the QoS counters. Okay. Okay, so again, the microbursts were totally absorbed by the switch, so it was a success. And now if we look at the queuing interface counters for that egress port, sorry, show queuing interface 143. What do we see here? We see, of course, a lot of packets still go to the QoS group 0, which is fine. Those are both some of the microbursts plus the elephant flow. Right, but if we keep going, we see how some of the first few packets, or maybe all packets here, were put in QoS group 7, which is a strict priority, to make sure the mice flows are being given the highest priority. Okay, so now let's focus on MicroBurst monitoring. So we're going to start with the same QoS policy as we had before. I have disabled the elephant flow for simplicity, and what I did is I have just resent the microburst. But you see, the challenge is if you use the traditional CLI, such as the show buffer CLI, what we see is interesting, but is fairly limited. We see pretty much only the queue, and we see the max number of cells that was used. And unless you're very lucky and you executed the CLI precisely at the time when the microburst happened, you would not see when it happened. And also you don't know what port was impacted. And you could come up with a software solution. You could do software polling and periodically execute the CLI, but probably you're not going to get something better than 1 second or maybe half a second, which is not sufficient to detect a microburst. So that's why the Nexus 9K EX has the feature called MicroBurst Monitoring. And so the way to enable it is to go to the QoS policy. So we're going to just reuse the QoS policy we have. And the CLI is called burst detect. And you specify two things, a rise threshold and a fall threshold. What it means is if we look at an example of a burst, we specify at what level we want a burst to be noticed. You could set the threshold to the lowest, which will allow you to detect the smallest burst possible. But the thing is, you might get overloaded by information if you have a lot of burst. And so it's up to you to find the balance. Maybe you want to set it to medium value, so you can see only the bursts that are meaningful, because probably the very short bursts, you can be sure they're going to be absorbed by the switch. But anyway, here for purpose of the demo, I'm going to set it to the smallest value, because I want to show you how precise it can be in terms of burst detections. Okay, and so now we're going to go ahead and go back here and resend the burst from Xia, and so as always it will take a few seconds. Okay, and so now if you want to see the microburst information, the CLI is called show queuing burst detect, and with detail you can get detailed information, which I have an alias for that one. And so we see it here now. So it just happened, and we see what egress interface was impacted by the burst, because remember we do egress queuing. We see the queue, which is here unicast Q0, and we see a start depth and a peak depth, right? Because we do hardware polling, but there is some interval at which we do it. So at the time when we start to see the burst, it might already have started. Okay, so here when we started to notice it, this was the number of bytes that were in this queue at this time. Okay, and this is the time when it started, and this is the peak depth, so this is the maximum amount of bytes we've seen in the buffer for this burst. So it corresponds to the peak value you can see here. Okay, and you can see at what time this peak happened. And here the end depth is 0, because at the time we noticed the burst simply stopped. Okay, and this is the time when it stopped, and so this is the total duration of the burst. Now this was actually a fairly long burst, but let's go to Xia and let's disable this one. And I have created a very small burst because I want to show you how small the hardware is capable of detecting. Okay, so we do the same pattern, right? We take two ports sending to a unique destination, both close to line rates, to make sure the buffer is going to be used. And so both flows use packets with 500 bytes in size, and the rate is line rate, and we send 500 of them from each ingress port. So 500 from this one, and also 500 from the second one, right? So if we do a quick calculation, right, it's a total of 1000 packets. The packet size is 500 bytes, so this is the total number of bytes that needs to be sent from the 10 gig egress. So in bits we do times 8, this is number of bits, and let's divide it by the speed, right? This is number of seconds, so this is 400 microseconds, which is a fairly short burst. So we're going to send it and confirm the switch is able to detect such a burst. Okay, so the burst happened. So let's check the CLI again. And we can see here the burst has been seen. Same interface. This is the start depth. This is the time, the peak, right? And we see duration is a little bit more, right? Probably because it's not exactly precise at the microsecond and we were not sending exactly line right. But what matters is the burst has been detected and we know the time and we know the peak number of bytes when the burst happened. Thank you for watching.